In this lecture, we want to continue our discussion of binary search trees and look at balanced trees. A balanced tree is one whose height grows at the rate big O of log n. Normally, we use the complexity classes such as big O to characterize the increase in time as the input size grows. However, the same idea can be applied in other areas such as additional storage that an algorithm might require, and also we can apply it to tree height. Thus, we can track the increase in the height of a tree and see that the rate grows at C log n, and that will provide a balanced tree. So the idea here is that the rate of growth of the height rather than the amount of time that it takes for the program to run. A balanced tree is not necessarily a complete tree. Recall that a complete tree has all levels full except possibly the bottom, and that bottom level that need not be completely full always has the nodes left justified. So a balanced tree is not a complete tree, and in fact there can be height differences between the left and right subtree that can be quite large but still falls into the category of balanced as long as the rate of increase in the height as elements are inserted remains in big O of log n. Balanced trees are actually designed to avoid the worst case behavior of binary search trees. You would never include a standard binary search tree in a library API provided to developers because of this worst case behavior. In the average and best cases, binary search trees perform very well indeed. Log n behavior is very good. However, the worst case behavior, which occurs when you insert things in order or in almost sorted order, in these cases the behavior descends to big O of n, and the difference between big O of log n and big O of n is rather dramatic. Big O of n is much worse than big O of log n. Therefore, balanced trees are designed primarily to avoid this worst case behavior. Balanced trees avoid this worst case behavior by restructuring the tree after an insertion or a deletion as needed to keep the height of the tree minimal. The most common method for doing this is called rotation. So it's a simple idea here. Looking at this tree, we can see that in this first case, the height is 2, 1, 2, but over here the height is 1. But it's the same 3 nodes. So in other words, I can take this 6 and pull it down. Now what matters is that everything to the left of the 17 is smaller than the 17. But the 6 can either be above it, i.e. the parent of the 17, or it can be the left child of the 17. Either position will work just fine. The trees are perfectly valid, but this has lower height. So what we want to do in these cases is where it's possible to reduce the height of a tree after an insertion or a deletion, then it is the effect you can cancel out the height increase from insertions. This has the effect of making the binary search tree, which is really balanced, a bushier tree. I'm going to switch over to the sketchpad and examine how this works. So we start here with a simple tree. And let's put 50, 70, and 30 here. Now I'm going to insert a 20. Can this tree be restructured in a way to reduce the height of the tree? And the answer is no, it cannot. The problem here is you have 4 nodes, but there's no way you can create a tree with 4 nodes in height 1, because no node can have 3 children. Therefore, no matter how you reorder or rearrange the nodes in this existing tree, you're always going to have a situation where you have to have height of at least 2. Now I'm going to come along and add a 10. And here we have height equals 3. 1, 2, 3. So there are 3 edges along this path, therefore it's height 3. However, we can restructure the nodes now. We can reduce this to height 2. And we do this by rotation. So what we're looking at, the general heuristic is you backtrack after an insertion and look at what has occurred to see if a restructuring can be done. You will then rotate the nodes involved. Notice that there are actually 3 nodes in play here. And it is this set of nodes that is in play. These 3 can be involved in a restructuring, and this will give me a tree that looks like this. 70 here is untouched. Off of this we have 10, and then here we have 30. So now the height here is 2. We have made this tree bushier, that is, and the height is less. Now I want to look at the piece here that we just worked with. We have 30, 20, and 10. And so, as we discussed previously, I can pull this 30 down without changing anything. I can turn this into 20, 10, 30. This is the same valid tree, except that the 30 has been pulled down. The 30 can be above the 20, i.e. its parent, or the 30 can be the right child of the 20. Either way works. The only requirement is that it be to the right side of the 20. And so in this case, it works in either position. So we do this rotation here and attach the new top. So this becomes the new root of this subtree, which is attached where the 30 was, and then we end up with the tree you see here. Depending on the type of balanced tree that you're using, when this happens, when it's invoked, differs. However, the mechanism remains the same for many of these balanced trees. So there are 4 cases to consider here. Cases 3 and 4 are more troublesome. The problem is just this. Looking here at this, 16, 17, and 22, I can pull the 6 down. But over here in cases 3 and 4, what am I going to pull down? There isn't really anything to pull down. Part of the problem is the fact that the median element is not in the middle here. In cases 1 and 2, the 17 is the median element and it's in the middle. Therefore, when you pull the 6 down, the median element is at the top. It was in the middle, so it's in between the smallest and largest nodes in this subtree. Here again, the 17 is in the middle. We can pull the 22 down, and that will satisfy this property required for a binary search tree easily. But that's not the case here, because the median element is not in the middle. The median element is here at the bottom. And this is obviously a problem. So we will have to do a double rotation to fix this issue. So we're going to do another example here. Suppose that we have 50, 30, and 70. And now I insert a 20. As we have previously discussed, this tree cannot be altered. I cannot reduce the height of this tree. But if I do another insertion down this left path, I'm going to create a tree that could be restructured to get a lower height. So the last time I put a 10, this time I'm going to put 25. So I think you can look here and see, again, These are the three nodes that are in play. These three nodes here. But the median element is at the bottom. What I need to have when I get done here is this. This is the only way I can put these three nodes and reduce the height. And so I need the 25 to be in the middle. So the idea for a double rotation is just this. I want to rotate these nodes, the 30, this direction. That is, I want the 30 pulled down. And so with a double rotation, you rotate the child node the wrong direction. We rotate the 20 to the left first. Now there aren't a lot of other nodes in play here. We have drawn the minimal tree. But I think you can see what's going to happen. If I pull the 20 down, the 25 goes up in its place. So what we have done is turned one of these cases into a different case that is easily resolvable. This is the effect of the first rotation. So I have moved this around, pulled the 20 down, the 25 comes up, and we are now left with this, which is one of our simple cases. Now we rotate the 30 to the right, and we have 50 at the root, the 70 which did not move. Here we now have the 25, 20, and the 30. So this is how a double rotation works. And this is the case. If you have a straight path such as this, then a single rotation will do. However, if it's not a straight path, the median element is not in the middle, then you'll have to do a double rotation. To do a double rotation, we examine this case. The three nodes in play here, 30, 20, 25. The 30 needs to be rotated toward the light side. That is, the height on this side is 2, 1, 2, but the height on the right side is 0. There are no children here. Therefore, we need to rotate toward the right side. To do this, we rotate the 20 the wrong way, to the left, and then the 30 to the right. So first we rotate the 20 to the left, which results in these three nodes. Then we rotate the 30 to the right, and we end up with this tree where the height is 2. We have reduced it by 1. So again, here are the four cases. These are just mirror images, one of the other. The key element to remember is if the insertion path is a straight line, and what we're looking at is the path that was followed for insertion. So in case 1, the 22 was just inserted, which created a situation where restructuring can help. In this case, the 6 was just entered. That was the last node in. And again, we have a straight line along the insertion path, and a situation where a rotation will help. In cases 3 and 4, we do not have a straight line along the insertion path. Restructuring will help. However, we need to do 2 rotations. So the first rotation would be the 6 rotated to the left, and then the 22 rotated to the right. So that first rotation, the 6 to the left, will pull the 17 up here, and then we will have precisely this case. Similarly with case 4, we need to rotate the 22 to the right and then the 6 to the left. So you're always rotating toward the lighter side. So rotate the child node the wrong way. The 22 goes to the right, which has the effect of pulling the 17 up here, and that gives you case 1. So this is how you can tell that a double rotation is needed. We do not have a straight line here. And so when we rotate the 6 to the left, we pull the 17 into position here, and we now have a straight line. And then we can pull the 22 down, which gives us a balanced set of nodes. The nodes to be rotated may have children attached to them, and this may be troublesome. So in the case of this tree, this is a case where the height of the tree cannot be reduced by rotation. That is, we can't arrange this in any way that will reduce the height from 2 to 1. That can't happen. However, if you think of this as being a small set of nodes in a larger tree where a rotation will help, that may be useful. This is just a smaller set. So we're focusing now on the rotation, and I want you to accept the notion that we need to rotate the 9 to the right. What I want to demonstrate is, what do you do when there's a node in the way? So if we rotate this 9, the 3 will become the new root, and the 9 needs to come down here, but there's a 6 in the way. With the 6 in the way, what do we do? So here I've pulled it down. This is where we need to go. Pulling the 9 down here, we have 1, 3, 6. The 11 comes along for the ride. It didn't move. It was the right child of the 9, and it still is. But what happens to the 6? It looks like it's orphaned here, and it has to go somewhere. So what can we do with this situation? So I want to take a look at this tree and look at what has to happen with this other node. We have 9, 3, 1, 6, and then an 11 here. So when we do the rotation and pull the 9 down, we will have 3, 1, 9, 11, 6. Notice the 6 has changed sides. This seems strange at first, but it's perfectly valid. The 6 must be to the left of the 9. Well, it is here. So what I want you to notice is that in between the 3 and the 9, this is the 9 that's coming down. So in between the 3 and the 9 is the 6. This 6 can go either way. It can either be left of the 9 or right of the 3. Either way will work. Well, the problem, of course, is I can't put the 9 here because the 6 is in the way, so I have to detach the 6. Then I pull the 9 down, and now the 6 gets attached on the other side, a left child of the 9. So again, the 6 is in between the 3 and the 9. In between the 3 and the 9, and it can go either place. It can either be to the right of the 3 or the left of the 9, and both ways work. So in these cases, when you do the rotation, if there's a node in the way, i.e. when you pull this node down, we have this situation. When you pull this node down, if there's something here, it will have to go to the other side. That is, it will become a left child of this node. So it will have to switch sides and go here. So the 6 is the right of the 3, and then it becomes left of the 9 in this case. So you can see here the effect of the rotation. The 9 needs to come down here, but there's a 6 in the way. So we merely attach the 6 to the other side of the 9. Here, in between the 3 and the 9 is the 6, and it can go on either side. So we use rotation to restructure the nodes in the tree and in doing so, we reduce the height by 1 while preserving the structural and ordering properties of the tree. So the effect here is that you can do a new insertion with a 0 height increase. Also, when a rotation is performed, a child node that's not part of that insertion path may have to be shifted to the other side. So this is the end of our first lecture on balanced trees. Some of these ideas may seem uncertain to you and a little fuzzy, but the actual implementation of this we will see in the next couple of lectures. Both AVL trees and red-black trees will be studied in this course, and both of them use exactly this rotation strategy. And so it's difficult to show exact examples here until we discuss those implementations, and I believe that this will come into clearer focus when we do that. So this is the end of the first lecture. Make sure that you understand this idea of rotation, and in particular what happens if there's a node in the way, and when a double rotation is needed rather than simply a single rotation.